Hello and welcome to this presentation on our paper, Automated Derivation of Parametric Data Movement Lower Bound for Affine Programs. So this is about an automatic tool that does an analysis of programs that belong to the class of affine programs and outputs a formula that is lower bound on the data movement of this program. So first, what does it mean to compute a data movement lower bound? And how does it differ from optimizing a program's I/O? So when you run a program on a computer, it's doing a certain number of CPU operations and a certain number of I/O operations. And depending on the relation between these two quantities, the program is either be computation limited if it does a lot of CPU operations. That means the bottleneck of the speed of the program is going to be the frequency of the processor, or it's going to be I/O limited, meaning the bottleneck of the speed of the program is the bandwidth of the memory. This can be represented on a single dimension using operational intensity, or OI, which is the ratio between these two quantities. If a program's operational intensity is low, then it's going to be I/O limited, and if it's high, it's going to be computation limited. The way you usually think about OI is that you have a program and you want to improve it using some program transformation. So an optimizing compiler can take a program, and then maybe if you're lucky, it will manage to do some tidying and output a program with a higher operational intensity. The transformation that it can do is basically change the schedule of operations and the way memory is allocated. On the other hand, IOLB, the tool we developed, proves that a program's operational intensity cannot be improved beyond a certain limit. So you have a program, you want to know whether it's possible to improve it, and IOLB will tell you, well, either yes, there is some room to improve it, or it will you no, there is no way you can do anything. So to sum it up, IOLB takes a C program and outputs a formula that is a lower bound on the I/O of the program, and it's a mathematical function of program parameters and cache size. Be careful, because I'll be talking about I/O and OI is the inverse of I/O, so an I/O lower bound translates into an operational intensity upper bound. A quick outline of the rest of the talk. So first, I'll give an idea of how to make a proof on to prove lower bound on I/O complexity and what is the model that is used, then how these proof techniques can be automated, a quick overview of the rest of the paper, and then the results we were able to get on a full benchmark. So IOLB does proofs, so we need a way to abstract an abstract representation of programs, and this representation is a graph called the CDAG, the Computational Directed Acyclic Graph. In this representation, vertices are computations of the programs, and edges represent the data flow of the program. That is, there is an edge between two vertices if the computation of one vertex requires the result of the computation of the other one. So here, the computations are identified with the data they produce, and for a single graph, there are multiple valid sequential schedules, and we do not take parallelism into account. So if we take this simple program with just two nested loops and a single statement, the corresponding CDAG for fixed values of the parameters n and m, but remember that IOLB outputs a parametric formula, so the CDAG is actually parameterized by these two quantities. So this CDAG is on the right, and so the nodes on the outside are the input arrays A and C, and the nodes in the inside, the black ones, are all instances of this instruction. For a given schedule for a program, we need to define the cost in terms of I/O of this program, and this is done in a very simple cost model, we have two levels of memory: a slow memory of unbounded capacity that you can think of as the RAM, and a fast memory of fixed capacity S that you can think of as the cache. And the cost of a program is the number of transfers that is done for a given schedule from slow memory to fast memory, that is loads. And the memory management, that is load and store, are done manually. There is no cache policy. Finally, we need to define the I/O complexity of a program, and this is the minimum cost over all possible valid schedules for a program. So to illustrate this, let's go back to our example program, and these are three possible schedules for the operations in this program. On the left in red, this is the original schedule of operations. So these are done row by row. First, for t equals 0, we go from I equals 0 to n minus 1, and then for t equals 1, etc., up to m. But the blue schedule is also a possible one. We just reversed the I loop, so we're still going by increasing t, but the I loop is by decreasing I. And since there is actually no dependence between nodes in the same row, any order for a given row could be done. And finally, this green schedule splits the program into columns and then does each of the column row by row. The question is which one is the best. So if a full row of the CDAC does not fit in the fast memory of size S, then the green, a schedule such as the green one will perform better because there will be more reuse between rows inside a column compared to doing full rows. However, we do not know whether another schedule might perform even better than the green one. And it is not possible to enumerate all possible schedules because there are way too many, so we need a way to prove that a schedule cannot perform better than some quantity. The way to prove this is with a technique called Spartitioning. On a very high level, the idea is to find an upper bound on the size of a subset of the graph that can be computed using some fixed number of loads. And if we can find that, then this will, by bounding the number of such sets, we will find a low bound on I/O. In terms of graph, this translates in finding a subset of the graph P with an inset that is vertices outside P that have successors inside P, with an inset that is of cardinality smaller than 2s. So now to find a bound of the size of P, we use a geometric reasoning. If you look at the CDAG of our example, it is naturally embedded in a two-dimensional space, and since dependencies are parallel to the basis axis, the inset cardinality can actually be bounded by the size of the projections of the set P. And when you have a bound on the size of all orthogonal projections of the set, you have a bound on the side of the set by mathematical inequality. And in our case, by bounding each projection of P by 2s, we get a bound on the size of P of 2s squared, and this gives a lower bound on the IOQ of nm over 4s. This can be generalized to arbitrary dimensions and more complex the dependencies. So we've seen how the mathematical ideas behind lower bound proof, and now we need to find a way to automate this. So the first thing we need is a representation that is more compact than the CDAG and that can fit in memory. This is the data flow graph, or DFG. In this representation, a single vertex of the TFG represents multiple instances, multiple vertices in the CDAG that are the instances of the same statement in the original program. And a single edge represents multiple edges, multiple dependencies in the original CDAG. This is made possible by restricting the class of input program to IOLB to only affine programs, that is, loop nests with static control flow and array accesses in which subscripts are affine functions of loop counters. The machinery behind this comes from the Polyhedral compilation community, and mainly we use the ISL library, and one of the main advantages of this representation is that it captures the geometric regularities in the computational graphs, allowing us to use the geometric reasoning that was presented earlier. So this was a quick glimpse of the way the IOLB works. This diagram shows all the steps that go on in this framework, and in red are the parts that I talked about in this talk. So if you want to have a broader view of the algorithm, you're very welcome to read the full paper. Finally, the results. So we were able to run IOLB on a full suite of benchmarks called PolyBench. It's made of 30 kernels that are all affine, and for each of these kernels, IOLB outputs a formula that is a lower bound on the I/O of the program. This directly translates into an upper bound on the operational intensity of the program. If you want to compare to previous work, for many of these kernels, no bound was previously published in the literature, and for some of them there was a bound that was obtained through a manual proof. And in comparison, IOLB is able to output automatically a bound for all of these kernels. For one of them, for matrix multiplication, this matches the best published bound, and for all other kernels, this is an improvement over what was previously published. Also, for almost half of the kernels in PolyBench, the bound output by IOLB can be matched by designing a manual schedule. So this means that the bound is tight and that the I/O complexity for these programs is now a closed problem. And all of this was done through an automated process. So to sum it up, IOLB is the first tool that is able to automatically produce an I/O lower bound for programs. It uses geometric reasoning and the polyhedral program representation, and is able to produce state-of-the-art results on a full suite of affine programs in the benchmark PolyBench. There is much more in the paper, so you're very welcome to have a look at it. Thank you very much for listening to this talk, and I will now welcome your questions.